Hi class, how are you doing? Video lecture 3 about to start here. I'm going to try and address some of the questions that you guys had in class. We'll be talking about Fourier series expansions, and I want to give you a few examples. These are examples or questions you solved in your homework, the last homework set, but just so you see how some of this integration works and to how to get it to the format that somebody asked in class, Rebecca. So far we already understand fully, I guess, how to. And this question here, by the way, is from section 12.2. After we covered Fourier series, we understand how to make expansions using appropriate orthogonal sets. For this section, we'll use the same orthogonal set that we had developed. Call that P, cosine n prime x over P. Okay. In class, we already learned how to use different kind of orthogonal sets, the Legendre set, the Bessel set. But today, we want to see how to use this one in particular. And hopefully, this is a good enough example to show how to manipulate those integrations. The form that we're looking for is f of x equals a naught over 2 plus the summation okay, so this is the Fourier series, and those coefficients are determined as 1 over p negative p to p f of x dx for the a0. Again, this is just the inner product of f of x with 1, the first orthogonal function, divided by its norm. A n was then, well, let's just find out what a0 is real quick. A0 is integral, so 1 over p, identify our p as pi, right? Remember how to do that? We know the overall interval is 2 pi, so 2p is 2 pi, and then p is pi. Okay, so since we know p is pi, a naught is 1 over pi minus p pi to pi f of x dx. Since this is a function with 2 different values for different ranges, we split the integral, going from minus pi to 0 dx, so 0 to pi x squared dx. Okay, this obviously goes to 0 because it's a constant when you integrate. And this one goes to x cubed over 3. There's still a 1 over pi outside. X cubed over 3 going from 0 to pi. And that is just pi squared. So pi cubed over 3 divided by pi. Pi squared over 3. Okay? So that's the first coefficient. 0. So let's have that recorded, pi squared over 3. The other coefficient for the cosine functions is again an integral of this form. The inner product of f of x and the cosine functions divided by the norm. Again, we've identified what p was to be pi. So this is easy to integrate, right? 1 over pi pi that's just cosine nx. Okay, again I split the integral Okay, minus pi to 0 for the 0 plus 0 to pi x squared cosine nx dx. Okay, this is 0 as before. This here, you can easily integrate as well, right? Using integration by parts. Let's say I call this u, I call this dv. That means my u is x squared, du is 2x dx. My dv is cosine nx dx, and my v is sine nx over n. Okay, so using that substitution, I can determine this integral as x squared times that going from 0 to pi minus this integral. That's u or v du, right? So that's 2x sine nx over n x. Okay. To evaluate this, plug pi in the sine n pi will always give you 0 for integer n, and sine 0 is always 0, so I get 0 here. Minus, now we'll do this by parts again. I'm just going to pull out the 1 over n. By the way, there is a 1 over pi outside here still. Okay, so I pull out the 1 over n and bring it along with the pi. Now I have 1 over n pi times this integral. Right? So I'll just rewrite that as 0 to pi 2x sine nx dx. Okay, so I then do by parts again. There's 1 over n pi. Now I have, let's just pull out the 2 as well. Now I have x, that's my u, that's my v, there's a negative sign, cosine nx over n, going from 0 to pi, minus 0 to pi again, and now my du is 1, so I have negative cosine nx over n. Okay, and then I'm left with, I can take this off. Yes, take this off. I'm left with negative 2 over n pi. Evaluate this at pi, I get cosine n pi. This is where one of you had a problem. Rachel, I think, had a problem with this. If you put cosine n pi in here, note that you either get 1 or negative 1, depending on if the integer is positive or negative, or rather even or odd. So for example, cosine 0 is 1, cosine pi is negative 1, cosine 2 pi is 1, etc. So for even numbers, for even n, I get a positive number. For odd n, I get a negative. So I can rewrite this as negative 1 to the n. Again, for even n, this ends up being positive 1. For odd n, this ends up being negative 1. So cosine n pi can be rewritten as -1 to the n. So I can then rewrite this as plug in pi, that gives me pi. I'll pull out this negative sign here. And I know that cosine n pi is what we just showed. Divide that by n. Okay, that's this term right here at the upper limit. For the lower limit, I have cosine 0, which is always 1. Okay, so minus that gives me, or if you prefer, I'll put out the negative sign. So I'm applying 0 times this, but 0 times anything is 0, obviously. So I'm just gonna have this there. Let's leave that alone there. Okay. And the second, so we've evaluated this one. The second one is when I integrate that, I get plus sine nx over n, evaluated at 5. Okay, so like before, sine of n pi is always 0, sine of 0 is 0. So an is simply negative or positive now, 2 pi over n squared pi. Well, let's just write it at 2 over n squared. This pi cancels this 2. And that's 1 to the n. This was 0. Okay? So an equals 2 over n squared minus 1 to the n. Okay, so my Bn coefficients was defined as this: inner product with the sine functions and divided by the norm. I know my p is pi, so just like before, I replace that, and now I can get my Bn as 1 over pi. The 0, the first integral goes to 0, and the second integral from 0 to pi x squared sine n x dx. Okay, so this here again I do by parts. Bn equals 1 over pi x squared cosine nx over n, and there'll be a negative sign there, minus of going from 0 to pi, minus this integral here, 2x, 2x times negative, which I'll bring out here as positive, cosine nx over n. Okay, so now Bn, if I evaluate this at pi, I get pi squared here, I get cosine n pi, which again we said was -1 to the n. So that 1 over pi minus pi squared over n, -1 to the n. Okay, so I'm factoring out this here this time. Evaluate at 0, I still get 0, so I don't actually need to put a second term. Okay, so this is fully determined. The second integral that I can do again by parts, that's just simply 2x sine nx over n, evaluated at 0 to pi minus integral of 0 to pi, the u, which was 2x, the u rather, is 2 times the v term, which is sine nx over n squared. Okay, we're almost there. So our Bn is then obviously, again, this goes to 0 from similar arguments. Sine n pi always equals 0 and sine 0 is 0. So now we need to do one more integration by step. Did I make a mistake in the previous one? I seem to remember doing just one integration part. Anyway, one more integration by step, I get integration by parts. Oh, we don't need integration by parts because it's a constant. Okay, so that integral is just plus 2 cosine nx over n cubed evaluated at 0 to pi. And finally, we can say that Bn equals 1 over pi minus pi squared over n, negative 1 to the n. Evaluated at pi gives 2 plus 2 to the negative 1 to the n over n cubed. And then evaluated at 0 is 1 plus 2 over n cubed. Okay? And those are your coefficients a0, an, and bn. And you can get your full. If you want, you could factor this even further, but it's not necessary. But if you want, I can write this as that's a nice way to put this. Let's try. Okay, I guess we can group these ones together. Over pi, negative 1 to the n, 2 over n squared minus pi squared. Okay, so this right here is this term, and this right here is this term. Plus 2 over n cubed as your Bn. So now we can plug this back into our full Fourier series expansion. And we have that as pi squared over 6, because we have a over 2, plus summation of n equals 1 to infinity. This coefficient right here times the cosine nx over n squared plus the Bn coefficients, which is just 1 over pi, whatever is in that bracket, sine nx. Okay, this one is a little longer than I hoped for, but hopefully the idea is understood from that example. Okay, let's try. Oh, well, sure. And if I were to evaluate, why did I wipe that off? If I wanted to evaluate f of the series at a point of discontinuity, the function looks like this. From minus pi to 0, this is 0. From 0 to pi, it's x squared. Okay, there's no discontinuity. Okay, evaluating the series at any point here gives me something easy to determine. We can determine the function at that point. Okay, let's try a different example. How about 10? This one has a discontinuity. Let's try 10. F of x equals 0 cosine x, going from minus pi over 2 to 0, and 0 to pi over 2. Okay, so again, we use the full Fourier series expansion, which you know the form already. I don't need to write it down. Determine the coefficients. A0 is 1 over p, negative p, f of x dx. Identify my p. 2p is pi, so p is pi over 2. Okay, so I can write this as 2 over pi. It's pi over 2, so pi over 2, f of x dx. Just like before, I break the integral into two parts. The first part is 0. So a naught is 2 over pi, 0 to pi over 2, cosine x dx, which is simply sine of pi over 2 is 1, sine of 0 is 0, so I have 2 over pi. That's my first coefficient. Okay, try that. Try that for the other coefficients, same form. I don't need to rewrite that anymore because you guys know how it works. Pi over 2